Okay. So now for the second lecture, we have to now go through some properties of DC motors. This is quite important because it's the central subject of our central topic of our subject, right, of our course. And that's one reason why we need them. And second reason, they just, all of this is practically useful, right? Same as being able to compute inertia of the motor model is useful, like stuff that I'm going to give you here is useful. So let's dive in. So first, let us consider the question of steady state, okay? Steady state. Steady state solutions are in general very important to understand. But, and let me, I guess, convince you with this example here, why steady state is important. So here is the dynamics of the motor with the payload. Okay, so what we saw previously, here we have a payload torque. Here I didn't specifically write inertia as a sum of two components. We do it implicitly. And also I don't have a reducer here again, so I don't have it explicitly, but we could have it implicitly, right? We could have divided this by n. This could have already have this component of the outside inertia. So this model is not incompatible with the reducer, okay? It's just not explicitly have it. Okay. Now consider steady state. What is steady state? Let me remind you, is when state variables do not change. So here, what I would say is omega is equal to omega star and is constant. And our current is constant, okay? So those two are constants. Okay. Now here's omega star, here's current, they're constant. That means that this component goes away, and this component goes away from our equation. Otherwise, they remain the same. Okay, so again, here's omega star, here's current. Good. So you could say that now we have equations in new variables. Or I guess, yeah, so we have equation, we still have like unknown variables. For example, this constant values of omega and I, you could say that those are unknowns. Or you could say that U and tau are unknowns, right? So the equation becomes about algebraic relations between those four variables. If two unknown, so if you know two, you can find the other two, okay? So this is basically a relation between sets of variables, okay? So the set of four variables. Two have to be known for the other two to be found out. Let's see this in action. So let's say we know desired value of angular velocity omega star. And let's say we know payload torque tau. Okay, very typical, right? We know payload torque because we can compute it. So we can easily compute it for like a fan, like a propeller. We can easily compute it for gravitationally induced payloads, torques, right? So quite easy, quite easy. And desired angular velocity is very typical for a variety of tasks. It's very typical to know desired angular velocity. And those are not mechanical things, right? They're mechanical quantities. Now we can solve the equations for current and voltage, so for electrical quantities, right? So let me go back. So unknown variables now become current and voltage. So those two become unknown variables, while the other variables become known. So notice it is quite like a change of perspective, right? This is just a constant, this is a constant, this is a constant, but those are, the rest ones are unknowns, okay? Good. This will be a triangle equation. As you can see, the first equation contains two variables, while the second only one. Since second contains only one, we can instantly solve it. Substitute in the first, solve it. So triangle equations are easy to solve. Okay, now let's see how the solution looks like. So the solution looks like this. We have our current, which is equal to F over torque coefficient times desired omega, and 1 over torque coefficient times tau. And here we have a whole huge expression for voltage. So before we go to voltage, let me just look at this expression for current and see if it is understandable. Okay, so F times omega, these two together represent clearly friction force, viscous friction. Okay, and it is a torque, right? Everything in the second equation for motor is a torque, right? Because there's a torque equation. It comes from the Euler dynamical equation for 2D case. Okay, so this is a torque, and we divide it by torque coefficient to get the current that will produce torque to compensate this one, right? So it makes perfect sense. Like this part makes perfect sense. This whole thing is just a current to compensate for friction torque. Okay. And this one is a current to compensate for payload torque. So that's it. Very, very, very understandable, this part. Okay. Now, this is more complicated. This is more complicated. Essentially, you could see it in this way, right? First of all, there are two independent quantities here. Like this is one quantity, and this is another quantity. Okay, so we could break this into two separate equations. For example, let us consider this brackets like Fr divided by C tau times omega star. Well, what happens is F times omega is again friction torque, okay? Divided by C tau is again current that compensates for this friction torque. Times R is the Ohm's law. So this is a voltage that is dropping on the resistor. So this whole thing that I showed you is just a voltage that drops on the resistor, which is associated with a current that compensates for friction. Okay, so complicated but readable. Okay. Now, what about this guy? So C omega C tau divided by C tau times this guy. Well, C tau divided by C tau is just, this just goes away clearly. And what we have is back EMF. So again, understandable. C omega times omega is back EMF. What is this? Well, again, tau divided by C tau is a current, but now that compensates payload. And multiplied by R, you get the amount of voltage dropped on the resistor associated with the current that compensates for the payload. So that's it. You can see it is complicated, but it is you can read it. It's not so difficult. Okay. And now you can see, for example, if you somehow want a current control, so you want to make sure that you have a current that can compensate for steady state payload and angular velocity. Here is your solution. If you want voltage control, so you specifically care about like you set voltage. Okay? And here is your voltage, right? And this you get by analyzing steady-state solutions. And steady-state solutions are not perfect because they're steady-state, right? They don't track trajectory. They just discuss what will eventually happen. But they're powerful because often enough you care to do point-to-point control, right? So from initial position to final position, and for your scalar variable to go from initial position to current final position, you often have something like this C-shaped trajectory, which there are various ways to achieve, but to do it, you often want to know the value of the variable here, like the value of the initial value of the variable. Okay, you know it as initial condition. What is the final value of your variable? If it is, for example, u associated with a certain tau and omega, here is how you can compute. So understanding these state equations is important, and they're not difficult, right? It's just basic algebra. Okay, now let us consider steady state equation, but when omega is equal to 0. So steady state, but we have 0 omega. So we have constant angle and constant current. Okay. Well, let's go back and just look. So what will happen when omega is equal to 0? Well, this goes away. This goes away. Okay. So equations become very simple. It's only payload. Okay. So in fact, what remains is current will be proportional to the payload. The coefficient of proportionality is 1 over c tau. So c tau will determine how much current you need to compensate for the payload. And here you have r divided by c tau. So still, it is the same logic as before. C tau decides how much current you need to compensate for the payload, and R decides how much voltage you need to compensate for the current that compensates for the payload. Okay, so it's again Ohm's law. All right, that's it. So for the case when angular velocity is 0, it is quite trivial, all of this. Okay. Just as one consideration, what I want to say is those values, c tau and r and tau, are very easy to know in practice. C tau is almost a table variable. Even if you don't know it for your motor, you can always make experiments to find it. It's not difficult to find. Okay. R, you can measure directly with a voltmeter, like multimeter. Okay. Tau is you can compute it usually very easy, right? So those are understandable variables. On the other hand, here F is not easy to find, not easy to find at all. Back EMF, not as easy to find. You can, and often it is also a table variable, but it's not as easy as other ones. Okay, so I just want to point out that here it is, those variables are very obvious, while those are slightly less obvious. Okay. Yeah. By the way, again, one last consideration, I guess. If you are going to do, if you're going to use techniques of recovering those coefficients by parameter estimation, often you would see lumped parameters. So often what you would estimate is not those like c tau and c omega, but their product. So again, it wouldn't be as easy to get c omega. Well, possible, of course. It's just not as easy. Okay. Now, let's consider the question of power, mechanical and electrical power. Okay. So electrical power consumed by the DC motor, we define it as P sub E. It is simply a product of current and voltage. Mechanical power associated with the payload is angular velocity times payload torque, okay? So how fast you rotate this payload and how much torque you counteract, you could say. Okay, so those are two powers. Good. To understand power power dynamic of this motor, what we can do is we can multiply steady state equations by I and by omega. Okay. So here is a steady state equation multiplied by I. This is the Kirchhoff's law multiplied by I. You notice it was Ri, now it is Ri squared. It was C omega, now it is Ci omega. It was U, now it is Iu. Okay. Now this equation was multiplied by omega. Okay. So it was F omega, now it is F omega squared. This is right, the friction. Here's the torque. So it was C tau I, now it is C tau I omega. And now here you have tau omega. Right. Notice that tau omega is our mechanical power. So this expression here describes mechanical power, minus we can fix the signs like this. Same way exactly, here is this electrical power. Right? So expression here defines electrical power. And we have two expressions, right? One for mechanical power, one for electrical power, for steady state solution. Quite useful. Now, what we can do is we can compute efficiency, which is the ratio of mechanical power to electrical power. Essentially, efficiency is like how much power, mechanical power, which is what we care about, do we get by spending a unit of mechanical or electrical power, which is what we pay. Okay. So this ratio is as what we wrote. So far, it just looks like a mess. It's not difficult to analyze, but it, is definite, is a correct formula. So that is nice. To analyze it, we could we could just make some observations. First, if this guy is 1 or approaches 1, it would mean the entire power that you input into the system, as voltage and current, is transformed into mechanical output. So it will be almost no losses. Okay, that's the first observation that we can have. Another one observation is that here we have this component in the denominator, which is essentially heat power of heating, how do we call it. So this is the power of heating of the resistor, how much resistor is heated. Here we directly have it. Okay. Okay. This you could call, I guess, power of back EMF. Yeah, if you want. Right. So this is associated with the resistor. By the same token, this guy is actually mechanical power associated with dry friction. Oh, sorry, with viscous friction. Okay. So viscous friction has a torque that produces multiplied by angular velocity, and you get a power. So how much power basically viscous friction saps from the system? This is what it describes. Okay. So this guy is power of heating. Okay. And the heat is dissipated in the motor windings, by the way. So it means that this is how much your motor will be heated up. And if you want to understand how to design a cooling system, this is very useful. This is very useful information because it will tell you how much heat is dissipated, by your motor. How much dissipation do you need to provide for the overall unit to dissipate all this heat into the environment? Okay, it's a very important question, especially since motors, as they heat up, resistance can change, parameters of the motor can change, so it's not very good. Okay, now let us assume that F, this friction coefficient, is very small. So this is negligible. By negligible, I mean it is negligible compared to this unit here, which is torque produced by the motor times omega. If it is negligible, the expression becomes like this. So what we have, and that is quite interesting. So let us consider this expression. That's quite interesting. So here, again, we have tau produced by the motor, associated with the current, and multiplied by omega. So this is basically a power, mechanical power produced by the motor, you could say, like not the power, mechanical power acting on the payload, but mechanical power produced by the motor directly. Okay. By the way, now they're the same because we assume that the friction force is negligible. So that was a trick. Good. Downstairs, here we have a power of back EMF. All right, no problem. Plus heating. Okay, plus heating. So if heating is higher, so we dissipate more energy in heat, this ratio will be lower. So the higher the heat, the lower this ratio. Makes sense, of course. Efficiency will be lower if we dissipate more power into heat. Perfectly understandable. Okay. Now, let us assume that the heating is small enough. So compared to, for example, the power of back EMF. Then we get even simpler expression. This ratio becomes this, okay? But notice, we have same element in both of them, I times omega. And I times omega can be cancelled, okay? So what we have in the final analysis is the ratio of two motor coefficients, C sub tau and C sub omega. So this explains to you what those coefficients are, what they mean. C sub tau and C sub omega, right, for a motor. They are directly related to the ideal case efficiency, okay? So if they're equal, the efficiency will be 1 if you don't have heating, if you don't have friction, which of course you always have heating and friction. But if you didn't have them, like friction, you can make it negligibly small, okay? Quite easy. Heating, again, resistance of the windings can be quite small. So then if your motor will, under those circumstances, be perfectly efficient, like close to 100%, that means that those two coefficients would have to be equal to each other. All right. So if your motor efficiency is close to 100%, those coefficients will be close to each other. Of course, if your motor is not close to 100%, then they don't have to be close to each other. But in this case, you have to kind of ask, is it because of friction? Is it because of heating or anything else? Okay. When you look at catalogs of motors, you would often find that those coefficients are equal. It will be surprising to you if you don't see this particular equation. Equation 13 explains why they're equal. Because the motors are, for example, Mach-Son motors, those types of motors, they're often close to ideal. Like the friction is small, the heating is small, so they're close to this ideal, kind of like no energy lost machine. Of course, no machine is 100% efficient, but they can be close to 100% efficient, right? It's like high efficiency. And this relation explains to you how this works in terms of coefficients. Okay. So somehow back EMF coefficient is equal to torque coefficient. Like, who would have thought? But yeah, from power, you can understand what's going on. Okay. So often when people model motors without like concrete knowledge, they just want to play around with numbers. They would assume that those two numbers are the same. Okay. That's a typical assumption. Okay. Now let's go back to this power equation. Okay, so we have electrical power equal to the power of heating plus power of back EMF, and here we have power of the payload equal to the power of produced torque minus power of viscous friction. Okay. Now, what happens if the shaft remains still? So omega equals to 0. Well, this goes to 0 clearly, and this goes to 0, right? So the second equation will be just like the power of payload is equal to 0. And of course, right, if payload doesn't move, of course the power is 0. Okay. The power is the rate at which the work is produced, and work is produced by motion. If it is still, then no work is produced, mechanical work. Now, what about the electrical power? Well, here, the only thing that's going to be cancelled is the power of back EMF, okay? The power of heating will still remain, all right? So there will be still a power of heating. Well, that means that while mechanical power is 0, electrical power is not, okay? And this means that entire power input will be converted into heat, which has to dissipate from the motor windings. Which scenario are we describing? Well, it is actually a very typical scenario. Imagine you use, okay, let me, for drawing, I'll make a white space here. All right. So imagine you use your motor. Here's your motor. I'm trying to illustrate. All right. Use your motor to keep something in place. Let's say it is a inverted pendulum. Okay, so here's your payload. Here's your vertical direction. I would note it in black. Okay, vertical direction like this. Now you have this angle. So you just want to fix this, this payload at an angle. So what you have is, I guess, torque produced by this force times this distance, right, to the line of action. This line of action is the axis. Great, nice. Here, I guess the way I draw it more correct, distance of the line of action is like this, right? I draw it in 3D, so this is, I guess, more correct. Okay, so what we have is non-zero torque, which means, remember we studied steady-state equations. Non-zero torque means non-zero current. Current cannot be 0. Current would have to be equal to torque divided by C sub tau. Okay, so we would have in this scenario non-zero current, and this current will produce heating. So when motor sits in this regime, it will spend its entire electrical power to generate heat. And the heat will have to be dissipated. If you don't dissipate it, you heat up the motor and it will break eventually. And efficiency is 0. Okay, so the efficiency is 0. Everything is dissipated to heat. The question of efficiency is not very important. It's just like something that we like to consider. But the fact that you generate enormous amount of heat, like, I mean, you can imagine your current can be quite sufficient. It's not going to be a very small current. It has to worry you because you warm up your motor at a high rate. Power of heating, it's a power, so it's acting over time. And if you're going to sustain this posture for a long time, you would accumulate quite a bit of energy, right? Power is the energy differentiates with respect to time, right? So if you integrate over time, you get back energy. So if you sustain a posture like this for a motor, you get energy from this power of heating. And this is not going to be very good for you. This energy has to go somewhere. If you want to sustain it, you have to have some kind of cooling system. Often people install cooling systems inside motors, but also often enough, those motors are, especially for some older motors, what happens is the rotation of the shaft itself rotates the fan that creates airflow through the system, allowing to get rid of some of the heat. But if you have a static position, no fan is rotating anywhere. So you have to be very careful about what you're doing. When you design systems which are supposed to sustain constant payloads like this, you have to be careful because the motor in this position would simply be like a heater, like electrical heater, okay? It just acts as a huge resistor. That's not exactly what your motor is designed to do. So you have to be careful. There are various ways to negotiate this. And one is very popular, I guess, in practice, is to have non-backdrivable gearboxes. So this will be the type of gearbox which completely negates payload. It would just, the motor wouldn't feel anything. It would just sit on the gearbox, and that's it. There are downsides to this type of approach. For example, there will be zero compliance in this case if you use non-backdrivable gearboxes. We will consider all the gearboxes in lecture 8, so wait a little bit and we'll get there. But for now, just remember this lesson about the heating. Okay. Now, what ideal reducer does? Let's consider ideal reducer. So not stuff that we just discussed, like not backdrivable things, but ideal reducer. What does it do? Well, it does not influence electrical power, okay? It just isn't even in the equations. So none of the equations even change when you introduce a reducer. Now, the output shaft is n times slower, and the torque is n times higher. So the power of the payload would be, this n times slower velocity times n times higher torque. So in fact, this n here will cancel with this n. So you notice it doesn't, ideal reducer does not influence mechanical power either. Okay, so this is the idea of ideal reducer. It does not change the power flow. It changes velocity and changes torque, does not change power. Okay. Of course, actual physical reducers do change power and always making it lower. This is like classical aspects of mechanics, which were recognized all the way back in Greece. Okay. Any machine can only decrease power. It can increase torque, but can only decrease power. Okay, so you cannot produce power out of thin air, and machines in particular don't do that. But they can increase torque, and that is good enough for us. Okay, so power loss of the reducer can be taken into account by considering viscous friction. Okay, for example, viscous friction. associated with the gearbox. So what we have been doing this whole time, F times omega, this component, it can be used to model the non-ideal aspects of reducer. Okay, in fact, power loss. So we don't have to do like a lot of additional work in this aspect. All right, and that is it. Here I suggest you to read this additional resource. This is specifically for efficiency. And the previous ones, I still suggest you to read them. They're pretty good. With that, we covered the basics of motors. Okay, we covered the basics of motors. So we can now move on to control. So 2 next lectures will have to do with control. It will be about general aspects of controlling systems of this type and PID control. So just in case, so you don't feel like, the following lectures will be a repetition of what you had on something like control theory course. Here, what we're going to do is we're going to consider what PID is. This is not something we considered in linear control, especially I component, what it does. We will see why it is needed, and hopefully we'll see it as a very clean picture. Whereas classical approach in like control theory is to consider system with arbitrarily many states. Here we have specifically a second order system, for which a lot of this becomes much cleaner and kind of simpler. This, simplifies the topic, but also it imposes on us the necessity to understand exactly what's going on. Not like in principle, like pole placement, you can place poles, but in particular, like what exactly you're doing, right? What exactly you're placing, what exactly you're making. So this is what we are going to spend time on in the next 2 lectures. So I hope we'll have your attention. All right, this is it for this lecture. Thank you for finding time to come.